press the bell icon on the YouTube app and never miss another update.
Hello students, today the last topic from D and F block elements. I would like to discuss about the topic about F block elements. F block elements. Already in last sessions we successfully finished that the general characteristics of D block and general properties of D block and preparation and properties of potassium permanganate and potassium dichromate with respect to the structures and uses. So, after the D block, next is F block elements. So, today the unit is the F block elements. The F block elements. What was the definition regarding F block elements? Differentiating electron enters into anti-penultimate shell of F orbital. Differentiating electron enters into anti-penultimate shell of F orbital is said to be what? F block elements. So, F block elements are also called as inner transition elements. Inner transition elements. Differentiating electron enters into anti-penultimate shell of F orbital. Ultimate shell S orbital, penultimate shell D orbital, anti-penultimate shell F orbital. After completion of 6s, 5d, 4f, that will be the energy levels. 6s, 5d, 4f configurations. These elements are also called as inner transition elements. These elements are also called as inner transition elements. So, what are the elements? What about the position of the elements in the periodic table? What will be the general electronic configuration, general oxidation states, atomic radii, ionic radii, and some chemical properties and uses. Now we have to discuss regarding inner transition elements, which are also known as F block elements. F block elements. So, here these F block elements are belongs to 3rd B group 6th period and 3rd B group 7th period. F block elements are belongs to which group? 3rd B, 3B group. So, here what is F block means? Differentiating electron enters into anti-penultimate shell of F orbital. So, F block 2 series, 4F series, 5F series. F block further divided into 2 series. F block further divided into 2 series. One is the 4F series, second one is the 5F series. 4F series elements are called as rare earths. 4F series elements are called as rare earths, and 4F series, total 14 elements are present in 4F series. Atomic number 71 to atomic number 58 to atomic number 71. Atomic number 58 to atomic number 71, Z is equals to 58 to 71, that is cerium, Z is equals to 58 to lutetium, Z is equals to 71. Cerium, Z is equals to 58 to lutetium, Z is equals to 71. These are total 14 elements. These are total 14 elements are said to be lanthanides, are said to be what it is? Lanthanoids. 14 elements are said to be lanthanoids. Atomic number 58 cerium to atomic number 71 lutetium. Atomic number 58 cerium to atomic number 71 lutetium, 14 elements. Total number of elements are 14 elements. These 14 elements are said to be lanthanides. Third B group, 6th period it is. 3B group, 6th period. 3B group, 6th period elements. Total number of elements 14. These are said to be lanthanides. Why these are called as lanthanides means the properties of the 14 elements are or these are resemble with lanthanum. The 14 elements are resembles with lanthanum. What is lanthanum? Lanthanum atomic number 57. It is belongs to D block element. The 14 elements atomic number 58 to atomic number 71, 14 elements are called as lanthanides due to these are resembles with lanthanum. And next one is Z is equals to 90 to 103, that is thorium, Z is equals to 90 to, and lawrencium, Z is equals to 103. These elements are called as actinides. 3B 7th period. 3B 7th period elements. These elements are called as actinides because of atomic number 89 is actinium. Atomic number 89 actinium, atomic number 57 lanthanum. The elements which are resembles with actinium as well as lanthanum. Due to that reason 58 to 71 14 elements are called as lanthanides, and 90 to 103 thorium to lawrencium remaining 14 elements are called as actinides. Lanthanides are belongs to 4F series, actinides are belongs to 5F series. Lanthanides are belongs to 4F series, actinides are belongs to 5F series. These elements which are placed bottom of the periodic table. What will be the position in these elements means bottom of the periodic table. Bottom of the periodic table. And here lanthanides are also called as rare earths. Lanthanides are also called as rare earths, and atomic number 92. 92 atomic number is uranium. Atomic number 92 is uranium. Greater than 92, Z greater than atomic number greater than 92 are trans uranic elements. Trans uranic elements. Atomic number Z is equals to greater than 92. What is 92? 92 atomic number is uranium. More isotopes element it is. Atomic number 92 is a uranium. After 92 the remaining elements are said to be trans uranic elements, and lanthanides 14 elements are said to be rare earths. Rare earths. And the position of the F block elements are bottom of the periodic table, and each period contains 14 elements. 58 to 71 lanthanides, 90 to 103 actinides. All lanthanides are resembles the lanthanum, actinides are resembles with actinium. Due to that reason they are said to be lanthanides and actinides, and both are belongs to F block elements. Lanthanides are 4F series elements. On other hand, actinides are 5F series elements. In these examples, in these elements, the differentiating electron enters into anti-penultimate shell of F orbital. Differentiating electron enters into anti-penultimate shell of F orbital. Due to that, these are called as F block elements, or also named as inner transition elements. F block elements and inner transition elements. And in olden days, what will be the source of this lanthanides means monazite sand. Monazite sand is source for lanthanides. So, source is nothing but it was the lanthanides are available from that mineral ore, it is monazite sand, that is. Monazite sand is only one and only the oldest source which are available for lanthanides. And here what will be the electronic configuration of these group elements? First we have to study detailed with lanthanides. The chemistry of lanthanides was detailed, but the chemistry of actinides was not in detail because of moreover all elements are man-made elements, all elements are radioactivity elements, not natural radioactivity, those all are artificial radioactivity elements, and artificial radioactivity elements half-life will be very fraction of seconds will be there. Natural radioactivity elements half-life will be more compared to artificial because all are made by man-made only. So, the chemistry of actinides will be a little bit difficult. So, due to that we have to discuss detailed information regarding the electronic configurations, atomic radii, ionic radii, ionization potentials, melting points, boiling points, densities, basic nature and chemical properties, uses of lanthanides. Because the chemistry of lanthanides was easy to expand, because all are not radioactivity elements, while going to the actinides those are radioactive. Due to that reason, first we have to discuss about the properties and behavior of lanthanides. What are lanthanides? What will be the use of that lanthanides? What are the chemical properties of that lanthanides? Now we have to discuss. So, this was a simple general information regarding F block elements. It was a simple common information. So, after this next one is lanthanides. Lanthanides. After that we required one more class for that, actinides and applications of D and F block elements. Actinides and applications of D and F block elements, we required one more class. That will be the end of this topic. So, here we have to revise some elements regarding lanthanides. Total 14 elements was there. 14 elements, some elements are difficult to pronounce and some elements are new for students, because of students what they think means what they students, according to students they thorough up to 20 elements. They thorough up to 20 elements and they thorough that P block elements, third group, fourth group, fifth group, sixth group, seventh group. While coming to D block and F block, they should thorough 3D series. While going to 4D, 5D, those elements are not in touch with students' mindset. Like that here also lanthanides also different element, not different elements, common elements, but due to the not in touch, due to the not in use, they become new. So, we should to avoid that we should revise at least 5 to 6 elements. Out of 14 elements, 5 to 6 elements are very important. Then we have to revise the properties of that 5 to 6 elements and oxidation states, ionization enthalpies. Now we will discuss. So, the subtopic is here lanthanides. Z is equals to 58, cerium, and Z is equals to 71, lutetium. It is cerium. Total 14 elements are said to be lanthanides. Before this, we know that Z is equals to 57, lanthanum. Z is equals to 57 is lanthanum. So, here after lanthanum atomic number 57, 57 plus 7, 57 plus 7, Z is equals to 64, 64 is called as gadolinium, 64 is known as gadolinium, we have to revise this because of for entrance we have to Must and should revise this elements, this type of elements. Gadolinium, Z is equals to 64, gadolinium, and 57 plus 7, 64. 64 plus 7 is 71. What is 71? We know that is 71 is a lutetium. 71 is a lutetium. 71 is a lutetium. And here 57, we know 57 is a lanthanum. 57 is lanthanum. 57 is lanthanum. Next, while going to the 58, 58 is a cerium. 58 cerium. Atomic number 58 cerium. And after that, you mark this one. This one is very, very important, gadolinium. And here before gadolinium, 3 elements are very, very important. Before gadolinium, 3 elements are very, very important. Those are europium, samarium, promethium. Remember it is europium, samarium, promethium. Europium is a 63, samarium 62, promethium 61. These are the atomic numbers. So my dear students, don't get neglect. That's why I was given simple technique. It is 57 lanthanum. 57 lanthanum, 57 plus 7, 64. 64 is gadolinium. 64 plus 7 is 71. 71 is lutetium. 71 is lutetium, and 64 gadolinium. Before gadolinium, the elements europium, samarium, promethium. Europium, samarium, promethium. And here before this 71, one more element is that is Z is equals to 70. Z is equals to 70, that is said to be YB. YB means ytterbium. YB is called as ytterbium. And after gadolinium, one more element we have to revise, that is 65, that is TB. TB is called as terbium. TB is called as terbium. So minimum we required these elements to revise, because of we expect questions from these elements only. Z is equals to 61 promethium, 62 samarium, 63 europium, 64 gadolinium, 65 terbium, 70 ytterbium, 71 lutetium. Before 70, one more element is there, that is Tm, thulium, dysbium, different type of more elements are there, total 14 elements. So out of that 14 elements we have to revise this. So 58 cerium, 57 lanthanum. 57 lanthanum, what will be the configuration of lanthanum? And one more point also keep in your mind, my dear students, this is while writing electronic configurations, you keep one point in your mind, that is xenon. Xenon atomic number 54. Very, very important this is. While writing electronic configuration, you should keep in your mind the atomic number of xenon is 54. It is a stable noble gas configuration. With respect to xenon, so what will be the general electronic configurations? General electronic configurations also you should keep in your mind. That is, first is the 6s, next is the 5d, later is 4f. 6s, 5d, 4f configurations takes place in lanthanides. 6s, 5d, 4f configurations takes place in lanthanides, and all electronic configurations, one point you should keep in your mind, that is xenon. Xenon is a noble state, noble gas configuration. So with respect to xenon, here once you observe, it is lanthanum atomic number 57, xenon 54, we know that, and the remaining one 6s2, 5d1, 6s2, 5d1. This was the electronic configuration of lanthanum. Lanthanum electronic configuration, xenon 6s2, 5d1, xenon 6s2, 5d1. Remember, this is very, very important. Xenon 6s2, 5d1. This is not a lanthanide, but it is the lanthanides are resembles with lanthanum. So that's why we can start from lanthanum only. While coming to the next one, cerium. Once you make a note regarding this cerium, give one star like this here, cerium. One star for cerium. Because why we should give star for cerium means here we have to write the electronic configuration of cerium. Simple, xenon 54, 6s2, 5d1, 4f1. This was a configuration of cerium. 5d1, 4f1. 5d1, 4f1. Very, very important. Make a note, my dear students. It is cerium electronic configuration. Cerium electronic configuration, xenon, 6s2, 5d1, 4f1. And once you observe here, Z is equals to 57 lanthanum. 57 plus 7, 64. While coming to the 64, what is 64? Xenon 54, 6s2, 5d1. Xenon 54, 6s2, 5d1, total 54 plus 1, 55, 56, 57. 57. What is atomic number is 64. Atomic number 64. Up to finished 54, 55, 56, 57. Still we required 7 electrons. That 7 electrons takes place in 4f7. 4f7. This is the electronic configuration of gadolinium. Once you observe what I am saying here, cerium 5d1, 4f1. Cerium 5d1, 4f1. Gadolinium 5d1, 4f7. 5d1, 4f7. Last lutetium. While coming to lutetium, see once you, that's why you should give star for this. Gadolinium you should give star. And lutetium you should give star. Coming to this one, xenon 54. Xenon 54, 6s2, 5d1. Xenon 54, 6s2, 5d1. 54, 55, 56, 57. 57, 71. 71 minus 57 will get 14. So here 4f14. This was a configuration of lutetium. (57) lanthanum 5d1. 57 lanthanum 5d1. 57 plus 7 64. Gadolinium 5d1. 64 plus 7 71. Lutetium 5d1. Cerium 5d1. Except these three elements, remaining elements doesn't have d electrons. Remaining elements doesn't have d electrons means suppose if you will go to 63 europium. 63 europium, what will be the electronic configuration of europium? Xenon, this is common, 6s2, 4d6, 54, 55, 56, see this, 57. See this, my dear students, this was a configuration of xenon 6s2, 4f7. 6s2, 4f7 is europium, and 6s2, 4f6 is samarium, and 6s2, 4f5 is promethium. These are the electronic configurations of promethium, samarium, europium. Promethium, samarium, europium. 6s2, 4f5, 6s2, 4f6, 6s2, 4f7. While coming to gadolinium, the gadolinium electronic configuration is 6s2, 5d1, 4f7. 5d1, 4f7. And the next one is the terbium. What is terbium configuration? Terbium configuration also same, 6s2, 54 plus 2, 56, 56 plus 4f9, 9 plus 2, 11, 11 plus 54, 65. See this, 9 plus 2, 11, 11 plus 2, 65. So here these are the electronic configurations. So what will be the general electronic configuration of F block means general electronic configuration n minus 2, F1 to 14, n minus 1, D0 to 1, NS2. n minus 2, F1 to 14, n minus 1, D0 to 1, NS2. So except cerium, gadolinium, lutetium, except cerium, gadolinium, lutetium, remaining all elements differentiating electron enters into f orbital. There is no electrons present in d orbitals. Cerium 5d1, 4F1, gadolinium 5D1 4F7, lutetium 5D1 4F14. Already we know that half filled electronic configurations and full filled electronic configurations are more stable than a partially filling electronic configuration. Once you observe removal of 3 electrons from this 2 plus 1, you should remove the 3 electrons, it becomes noble gas configuration. Cerium, lanthanum 3 plus noble gas configuration. See this, lanthanum 3 plus noble gas configuration. While coming to the last example, lutetium, removal of 1 electron from this, removal of 2 electrons from this, then what you will get? Lutetium 3 plus F14 configuration. Lutetium 3 plus is what? F14 full filled electronic configuration. Full filled electronic configurations, and remove 3 electrons from this, gadolinium 3 plus half filled electronic configurations. Half filled electronic configurations, full filled electronic configurations are more stable than partially filling electronic configurations. So we require more energy to remove an electron from outermost. Due to that, half filled configurations and full filled configurations are more ionization potentials compared to partially filling electronic configurations. Clear it is. So here, that's why you should remember these, at least these elements electronic configurations. These elements electronic configurations are very, very important, because of based on this we have to decide some properties. Based on these electronic configurations we have to decide some properties. So make a note, my dear students, that is why you should give 57, 64, 71. 57 lanthanum and followed by 58 cerium. We know that 57 plus 7 gadolinium, 64 plus 7 cerium. Gadolinium half filled electronic configuration in ground state, cerium full filled electronic configuration in ground state, and lutetium full filled electronic configuration in ground state, and cerium only 1 electron present in ground state. Once you observe, while coming to the cerium, now we will discuss some properties regarding this lanthanides. So here, before starting, again we should require this electronic configurations to express the properties. What are the properties means? Generally, first is oxidation states, and atomic radii, ionic radii, and ionization potentials. Now we have to discuss. So here, this will be the general basic important explanation regarding lanthanides. So I hope you understood. So make a note and write these electronic configurations. Write these electronic configurations or take one screenshot. It was useful to you. So make it fast. Then after that, next we have to go to discuss about the oxidation states. So here, this will be the electronic configuration N-2 F1 to 14, N-1 D0 to 1, NS2. So here, generally lanthanides atomic number Z is equals to 58 cerium to Z is equals to 71 lutetium, total 14 elements. So here Z is equals to 57 is lanthanum. These lanthanides are represented, the symbol is Ln. The symbol which can use it for lanthanides is Ln. This is a symbol for lanthanides. Ln. Ln means, imagine it is lanthanide. Lanthanide means any one element. Cerium, lutetium, gadolinium, promethium, europium, samarium, terbium, ytterbium. Any one of the element you consider, lanthanides are symbolized by the letter Ln. Ln. So here, oxidation states. So common and stable oxidation state. Is +3. Very, very important. This is lanthanides common oxidation state and stable oxidation state is +3. +3 lanthanides are stable, trivalent. trivalent ions, trivalent lanthanide ions. So Ln plus 3 stable, Ln plus 3, what is Ln? Ln is called as lanthanides, Ln is called as lanthanides. So which is stable electron, stable oxidation number is, lanthanides are stabilized by the plus 3 oxidation state, lanthanides are stabilized by the plus 3 oxidation state. So here according to the oxidation states we have to discuss some points. Let us consider cerium. Cerium atomic number 58, electronic configuration is 6s2, 5d1, 4f1, Xenon. It was the electronic configuration of cerium. Cerium 58 atomic number is 58. We should write 6s2, 5d1, 4f1. Ce4 plus, Ce4 plus, cerium 4 plus. Cerium 4 plus is what is configuration? 6s0, 5d0, 4f0, only it is a Xenon 54. Which configuration this is? Noble gas configuration. Removal of 4 electrons. Removal of 4 electrons from outermost, 2 from s orbital, 1 from d orbital, 1 from f orbital. Then cerium can lose 4 electrons, gives rise to, cerium gives rise to cerium 4 plus 4 electrons. Cerium 4 plus 4 electrons, this is what configuration? Stable electronic configuration. Stable electronic configuration means a noble gas configuration. Stable electronic configuration is called as what? Noble electronic configuration. Here, but lanthanide is common and stable oxidation state is plus 3. But in this example, cerium oxidation state is plus 4. Plus 4 is unstable. Stable electronic configuration. Stable electronic configuration is nothing but noble gas configuration. But oxidation state, which oxidation state stable by lanthanides? Plus 3 oxidation state stable. But in this example, cerium exhibit plus 4 oxidation state. So for stability, it again cerium 4 plus gives rise to what? Cerium 3 plus. Stable oxidation state for lanthanides plus 3. Stable oxidation state for lanthanides plus 3. So cerium plus 4 is converted to cerium plus 3. So here oxidation number plus 4, here oxidation number plus 3, plus 4 to plus 3 decreases. Decreases means which reaction it is? Reduction. Reduction reaction. The species which are involving in reduction is called as oxidizing agent. Cerium 4 plus is which agent it is? Oxidizing agent. Very important, my dear students, make a note this is. Cerium 4 plus noble gas configuration. Cerium 4 plus on removal of 4 electrons from 2 electrons from s orbital, 1 electron from d orbital, 1 electron from f orbital, we will get cerium 4 plus noble gas configuration. And but cerium 4 plus is converted into cerium 3 plus. Why 4 plus convert into 3 plus? Because of stable oxidation state is stable oxidation state for lanthanides plus 3. Conversion of lanthanide cerium 4 plus to cerium 3 plus. 4 to 3. 4 to 3 means oxidation number decreases. Which reaction is? Reduction reaction. A species which are involving in reduction is called as oxidizing agent. Cerium 4 plus is oxidizing agent. Cerium 4 plus is oxidizing agent. This point keep in your mind, my dear students, very important. Cerium 4 plus is oxidizing agent. And one more point also there regarding this. Cerium 4 plus, the electrode potential of cerium 4 plus to cerium 3 plus is equals to 1.74 volts. The electrode potential 4 plus to 3 plus couple it is. The electrode potential of cerium 4 plus to cerium 3 plus is 1.4 volts, 74 volts. Due to that high electrode potential, it is act as oxidizing agent and it is used as analytical reagent. Analytical reagent. So it is used as analytical reagent. So cerium 4 plus to cerium 3 plus. So interconversion 4 plus to 3 plus reduction. Species involving in reduction is called as oxidizing agent. Cerium 4 plus is oxidizing agent. Cerium 4 plus is oxidizing agent. This is point number 1. Common oxidation state plus 3. Stable oxidation state plus 3. Lanthanides are denoted by the symbol is Ln. Ln plus 3 is stable. Cerium 4 plus act as oxidizing agent. Cerium 4 plus act as oxidizing agent. Because of cerium configuration is 6s2, 5d1, 4f1. Removal of 4 electrons from this will get 6s0, 5d0, 4f0. Noble electronic configuration, noble gas configuration. So this is point number 1. And next one, after this cerium, next is a Europium, EU, and Terbium, TB. Europium, Terbium. While coming to the next Europium, Terbium. Europium, Terbium is how to find the atomic numbers. It will be a little bit difficult. Due to that, what I said, 57 lanthanum and 57 plus 7, 64 gadolinium, 71 lutetium. Before gadolinium I said 3 elements: europium, samarium, promethium. Europium, samarium, promethium. After gadolinium is terbium. So gadolinium atomic number 65, europium atomic number 63, except lutetium, gadolinium, lanthanum and cerium. Remember this: lanthanum, cerium, gadolinium and lutetium. D electrons takes place. Remaining all elements doesn't contain d electrons. So here what will be the configuration of europium? Europium configuration, atomic number europium Z is equals to 63, we should write. Xenon 54, we know that. Xenon 54, 6s2, 5d0, there is no d electrons in this one. 54 plus 2, 60, 54 plus 2, 56, 56 plus 4f7, 56 plus 7, 64. So europium over it is. Next terbium, europium and terbium Tb 4 plus. Europium and terbium, terbium 65, terbium 65 we should write xenon 54 and 6s2 common, 5d0, 54 plus 2, 56, 56 plus 4f9, 9 plus 2, 11, right. So it is the electronic configuration of terbium. It is electronic configuration of terbium 65 and europium for 6s2, 4f7, 6s2, 4f7. So here europium, terbium and one more element also there, that is YB. YB. YB is called as ytterbium. Where ytterbium is there? So here this is Z is equal to, this is lutetium and YB it is. This is 70. YB 70. YB 70 is called as ytterbium. Ytterbium configuration also we should write xenon 54, 6s2 and 5d0, 54 plus 2, 56, 56 plus 16 we required, 16 plus 16. So 4f14, 4f14. So to avoid these confusions, what to do means we have to make one plan. According to plan only we have to take one step, we have to go forward. That's why I said 57, 64, 71. 57 lanthanum, 64 gadolinium, 71 lutetium. Before lutetium, ytterbium. Before gadolinium, europium, samarium, promethium. Europium, samarium, promethium. 57 lanthanum, after lanthanum, cerium. Lanthanum, cerium, gadolinium, lutetium. Lanthanum, cerium, gadolinium, lutetium, only these elements contains D1. D1. Remaining all elements doesn't have D configurations, D0. So here what will be the important point regarding this? So europium. Europium electronic configuration 54, 6s2, 5d0, 4f7. Ytterbium 70 atomic number it is. We should write Xenon 6s2, 5d0, 4f14. No need to add 0. 5ds, there is no 5ds. So here only 4f7, 4f7, 4f14, right. And next is terbium. This is terbium configuration. Here on terbium is there, and here cerium, we know that cerium is equals to 58, xenon 54, 6s2, 5d1, 4f1, 54, 55, 56, 58. So here, remember my dear students, I will give some points, explain some points regarding this, are very very important for entrance point of view. So don't neglect this. Here according to the electronic configurations, Europium, Terbium, we want EU2 plus, Europium 2 plus. Europium 2 plus means removal of 2 electrons from s orbital. Removal of 2 electrons from s orbitals, what will be the configuration? EU2 plus configuration 6s0, 4f7. It is a half filled electronic configuration. EU2 plus Europium half filled configuration 6s0, 4f7. Next Terbium YB4 plus, YB2 plus. YB2 plus, what is configuration YB2 plus? 6s0, 4f14. It is a fulfilled electronic configuration. 6s0, 4f14 fulfilled electronic configuration. And TB4 plus, once you observe TB4 plus, removal of 2 electrons from this, then we will get 6s0, 4f7, TB4 plus, xenon, just a minute, we should write here. EU is equals to xenon 54, 6s2, 4f7, and EU2 plus xenon 54, 6s0, 4f7. It is a half filled. And next is Terbium YB, atomic number 70, xenon 54, 6s2, 4f14. Terbium 2 plus, xenon 6s0, 4f14. It is a fulfilled. So half filled electronic configurations, full filled electronic configurations. And right side TB is equals to 6s2 and xenon 54, 6s2, 4f9 and cerium. Next TB4 plus, what is TB4 plus means? Xenon 54, 6s0, 4f9 it is, half filled. And cerium 57, xenon 54, 6s2, 5d1, 4f1, and cerium 4 plus, xenon 54, 6s0, 5d0, 4f0 it is noble gas configuration. So according to these configurations, before this you should remember this point, common and stable oxidation state is +3. Lanthanides common oxidation state, stable oxidation state is +3. While coming to the EU2 plus, Europium 2 plus, half filled electronic configuration, Terbium 2 plus, full filled electronic configuration, Tb4 plus, Terbium 4 plus, half filled electronic configuration, Cerium 4 plus, noble gas configuration. But what will be the stable oxidation number is +3 stable oxidation number. EU is available in 2 plus, EU2 plus unstable, so it is converted into EU3 plus, and YB2 plus converted to YB3 plus, because +3 oxidation state is stable, so here Europium 2 plus convert to Europium 3 plus, Terbium 2 plus converted to Terbium 3 plus. On other hand, we will come to this TB4 plus converted to TB3 plus, and CE4 plus converted to CE3 plus. Here in these examples oxidation number decreases, in this example oxidation number increases. Here oxidation state increases means oxidizing reactions, here oxidation number decreases means reduction reactions, and species which are involving in oxidation is reducing agents and reduction in oxidizing agents. So what will be the final point regarding this means Europium 2 plus, Terbium 2 plus are strong reducing agents. Europium 2 plus, Terbium 2 plus are strong reducing agents. Europium 2 plus actually half filled configuration, Terbium 2 plus full filled configuration, but stable oxidation number of lanthanides are +3. Stable oxidation number of lanthanides are +3. So conversion +2 to +3 oxidation reaction, species which are involving in oxidation is said to be reducing agent. So EU2 plus, YB2 plus act as reducing agents, and TB4 plus, CE4 plus act as oxidizing agents. TB4 plus, CE4 plus act as oxidizing agents. Common oxidation state +3, stable oxidation state +3, along with +3 some elements are exhibit +2 and +4 oxidation states, +2 and +4, here +4 oxidation state, here +2 oxidation state due to the half filled and full filled electronic configurations. This +2 +4 oxidation states you found in oxides only oxides we found +2 and +4 oxidation states. So here stable oxidation state +3. After from that you should revise, this is very important. Europium 2 plus reducing agent, cerium 4 plus oxidizing agent, Terbium 2 plus 4 plus Terbium 2 plus reducing agent, and what about that Terbium 4 plus oxidizing agent. Why oxidizing agents, why reducing agents? Because of the stable oxidation states. So due to that the electrode potentials of cerium 4 plus to cerium 3 plus, already I said that is 1.74. Due to that it is used as a analytical reagent. It is Ce4 plus Ce3 plus electrode potential is 1.74 volts. Due to that is used as analytical reagent. Cerium 4 plus used as analytical reagent. Higher oxidation states, actually our target, our stable oxidation number is +3. More than +3 are oxidizing agents, less than +3 are reducing agents. That point keep in your mind. Clear? +3 is stable. Some elements exhibit more than +3. The more than +3 act as oxidizing agents. Less than +3 act as reducing agents. Whatever the examples was given, which of the following lanthanides are reducing agents? Which of the following lanthanides are oxidizing agents? Means simple one mark will be there. One what is a common parallel line? One branded line means that branded line is +3. Above +3 oxidizing agents, while below +3 are said to be reducing agents. So common oxidation state is +3 and common and stable oxidation state, and these lanthanides are denoted by the letter is Ln. Lanthanides are denoted by the letter is Ln. And moreover trivalent lanthanides are color due to the formation of unpaired F electrons. All are the colors. in solid state as well as in aqueous state. In solid state, aqueous state, all lanthanides are exhibit color. Some exceptions are there. What are the exceptions? Means F0 configuration colorless, F14 configuration colorless. Remember here which configuration this is? YB2 plus which configuration? F14 configuration colorless because of full filled electronic configuration. CE4 plus what is configuration? CE4 plus 6S0, 5D0, 4F0. F0 configuration of CE4 plus, F14 configuration of YB2 plus, these are colorless. Lanthanum 3 plus, lutetium 3 plus colorless. Lanthanum 3 plus colorless, lutetium 3 plus colorless because 0 configuration, F0 configuration. On other hand, next we have to go to YB2 plus and LU2 plus, YB2 plus. If you take YB2 plus 14 full configuration, and next one is LU4 plus lutetium. Lutetium, where it is? Lutetium 2 plus. YB2 plus LU2 plus F14 and La3 plus and lanthanide LU3 plus F0. So F0 configurations, F14 configurations are colorless. F0 configurations, F14 configurations are colorless, and except F0 and F14 configurations, remaining all are exhibit paramagnetic behavior due to the presence of unpaired electrons. So here these are the general oxidation states and color property of lanthanides. Except F0, F14 electronic configurations, remaining all are exhibits colors as well as remaining all are paramagnetic. From this you should revise the points: Europium 2 plus, Terbium 2 plus or less than plus 3 species are reducing agents, more than plus 3 species are oxidizing agents. And especially you should make a note for gadolinium. Gadolinium is a very good example for half filled electronic configuration. GD3 plus gadolinium electronic configuration is, we know that is 6s2 5d1 4f7. 6s2 5d1 4f7, remove of 3 electrons, 2 from s orbital, 1 from d orbital, then we will get 4f7. So gadolinium 3 plus half filled electronic configuration more stable. So you should make one mark for gadolinium because of after gadolinium terbium, before gadolinium europium, samarium and promethium. Europium, samarium, promethium. So you should revise that elements, then you will get idea about this. And after that general property, we know that it is atomic radii and ionic radii. So some species act as oxidizing agents, remaining species are act as reducing agents, and next is atomic radii, ionic radii. So from left to right atomic radii decreases, we know that. From left to right atomic radii decreases due to the increase in nuclear charge. And gradual decrease, already we discussed in D block elements regarding this atomic radii influenced the screening effect, or I said that is a shielding effect, So here what we have to discuss regarding atomic radii means from left to right, that is cerium to lutetium, size decreases. Size decrease due to what? Increased nuclear charge. Because lanthanides are antipenultimate shell, differentiating electron enters into antipenultimate shell. After 6s, after 5d, next electron enters into 4f. After 6s, 5d, 4f. And one more point was there regarding before this 4f, next here it is 3d. FF screening is less. The screening effect one F orbital screens one more F orbital, but it screens less compared to one d orbital to another d orbital. One d orbital to another d orbital screening effect is more, but one F orbital to another F orbital screening effect will be less. Clear it is. So here imagine this is a nucleus. It is a 1s, 2p, right? 1s, 2p, 3d, 4f, 5d, 6s. So our target is this level, 4f level. After completion of 6s, next electron to 5d1, only 3 cases. Later it is a 4f. FF screening will be less compared to DD screening. FF screening is less compared to DD screening. After 3D here 4D will be there, here 5D will be there. After 5D only, for 4D will be there, 5D will be there here. After 5D only electron enters into 4F. After 5D only electron enters into 4F. So here once we observe one contraction takes place. That contraction is called as Lanthanide contraction. Lanthanide contraction takes place in as atomic number increases, the size will be decreased actually. The size will be decreased, but due to this Lanthanide contraction, some elements which are belongs to 4D series and 5D series elements. This contraction is affected by D block elements. Some elements 4D series and 5D series, those are already I said in zirconium, hafnium, niobium, tantalum and molybdenum, tungsten, same size. What will be the reason is lanthanide contraction. Due to the lanthanide contraction, zirconium, hafnium and niobium, tantalum and molybdenum, tungstens are having same size, because zirconium, niobium, molybdenum are 4D series elements. Hafnium, tantalum, tungsten are 5D series elements. From 4D to 5D size actually we expect increase. Instead of that, the increment will be not found in 4D to 5D due to the 4f electrons. 4f electrons are peculiar shape, not protect outermost electrons from nucleus attraction. Protecting power more for d orbital compared to f orbital. Compared to d orbital, p orbital, next s orbital. Penetrating power s greater than p greater than d greater than f, like that. So here due to that poor screening effect, why f orbitals are poor screened? Because of peculiar shapes. Due to the peculiar shape, f orbitals are not screened properly. Due to that we found lanthanide contraction. Due to that lanthanide contraction, some elements zirconium, hafnium, niobium, tantalum, molybdenum, tungsten all are in same size. So here one in textbook one graphical diagram was given, that is with respect to the ionic radii versus lanthanides. Ionic radius versus atomic number. You observe this graph, then one graph like this, x-axis ionic radius and y-axis atomic number. You will get like this one curve, like this, like this curve. You will get one curve, that is here lanthanum, cerium, gadolinium, lutetium, terbium, what about that terbium and europium, samarium and promethium, praseodymium, dyspium, different type of elements are there. So it is a +3, lanthanum +3, cerium +3, promethium +3. Simple here like this graph you found in NCERT text. Like this graph you found in NCERT text. So it is ionic radii versus atomic number. So while what happens here, as atomic number increases, ionic radii decreases. Ionic radii and metallic radii decreases. Ionic radii and metallic radii decreases because of FF screens will be less compared to DD screens. Compared to FF and compared to DD screens. One F orbital, one 4F orbital light screen to another, but one 3D orbital more screens to others. Due to that a gradual decrease we found from lanthanum to lutetium, and this will be explained in the form of lanthanide contraction. This lanthanide contraction is influenced by the 4D series elements and 5D series elements, and 4D series 5D series we expect size will be increased, but instead of that the size is becomes normal due to lanthanide contraction. So, this will be the end of this session. Still we required 2 sessions to completion of this. So, I hope you understood. Stay with us, stay safe, and if you are getting any doubts, please share your doubts, and please subscribe, and please press like button if you are like this video, and share your comments.